now we will be talking about the extrinsic semiconductor. So as we have seen that intrinsic semiconductor, since we have not got that much of electron and holes, okay, so we can say that it has got a little current conduction capability. So I am writing here that it has got little current conduction capability at room temperature. So when we are talking about the with respect to the electronics applications, what we are trying to say is that we have to alter the conducting capabilities of these devices. So what we are saying is that we have to alter the properties of a intrinsic semiconductor. And when we are talking about the alteration properties, we are referring to the that we want to significantly increase its conducting properties. Okay, because what we want that the current should flow through our material. Okay, so here we are using a semiconductor material, so we want that the current should flow through our semiconductor materials. Okay, it should be fast like a conductor. So we are significantly increasing its conductivity, or we are saying a conducting properties. So now the question is how you will going to alter the properties of intrinsic semiconductor. So the reason how we can alter the properties of a semiconductor is that this can be achieved by adding small amount of I'm writing by adding small amount of suitable impurities. Okay, we will going to discuss in coming lectures that what are the suitable impurities we are using. So small amount of suitable impurities in a semiconductor. And when we are adding this impurities to a semiconductor, okay, this process is known as the doping. Okay, so I'm writing here adding of impurities to a semiconductor is known as doping. And I will going to highlight this word doping. Okay, so this is very important when you want to make or you want to change the properties of a any pure semiconductor or an intrinsic semiconductor. Therefore, when we are talking with respect to the adding of a doping, it is also known as the impurity semiconductor or extrinsic semiconductor. So I'm writing it is known as impurity or extrinsic semiconductor. Thus, we can say that the purpose of adding impurity is to increase the number of free electrons or hole in a semiconductor crystal. So I'm writing it that what is the purpose of adding the impurity. So let me highlight this adding a impurity with a blue color. So adding the impurities is being done to increase the number of free electrons or number of holes in semiconductor crystal. So depending upon the type of impurities, okay, we have already seen in the previous lectures that we are talking about the group 3 and a group 5 elements. Okay, so when we are talking about the two types of impurities, so I'm writing when we talk about the types of impurities, the first type of impurities which we are talking about is the pentavalent impurities. So I'm writing here pentavalent impurity. So the pentavalent impurity means which will going to have a 5 valence electrons in it. So I'm writing in bracket having 5 valence electrons. And the second type of impurities which we are adding is the trivalent impurities. So I'm writing trivalent impurities. And trivalent impurity means that which has got 3 valence electrons. So I'm writing in a bracket having 3 valence electrons. So what we can say is that depending upon the types of impurities we are adding, we can define the semiconductors, that what types of semiconductor we are using. So I'm writing here, so depending upon the type of a impurity, we classify semiconductor as n-type semiconductor and p-type semiconductor. So when we are talking about the n-type semiconductor, what we say that we are using the silicon and the germanium along with the group 5 elements. Okay, so we can use either the silicon or a germanium with the group 5 element. And when we are talking about the p-type semiconductor, we are saying that we are using the silicon and germanium with the group 3 elements. So we can say that in n-type semiconductors, electrons are the majority charge carriers and holes are the minority charge carrier. So let me write it. Electrons are majority charge carrier and in p-types, holes are the majority charge carriers. And in p-types, electrons will be the minority charge carrier. Okay, so right now we are talking with respect to the majority charge carrier only. So we can say in n-type, electrons are the majority charge carrier and in p-type, holes are the majority charge carrier. And we have seen one of the law in an intrinsic semiconductor that N was equal to P equal to Ni. Okay, and now since we are talking with respect to the number of holes and number of electrons, now the number of electrons and number of holes are changed. Okay, so we will be using a formula which is known as the mass action law. So I'm writing here mass action law, and it say that the product of N P is equal to Ni square. So number of holes multiplied by the number of electrons will be equal to Ni square. Okay, so this is the formula which will be valid for the extrinsic semiconductor.